Welcome to the class, dear students. Today we are going to study about acidity of phenol. Phenol, the structural formula of phenol is this, right? And then what is the molecular formula? C6H5OH, right? Phenols are acidic in nature. They are acidic in nature. They are weakly acidic. They are not strong acids. They are weak acids. So they are acidic in nature. Why they are called as acidic in nature? Let's see that. Phenol, when they dissolve in water, they release H plus ion. Fine, they release H plus ion, and those compounds which when dissolved in water, when they release H plus ion, such compounds are referred to as Arrhenius acid. What are they referred to as? Arrhenius acid. So because phenol, when it is dissolved in water, because it releases H plus once it is dissolved in water, therefore phenol is Arrhenius acid. Phenol is a Arrhenius acid. Okay, so such compounds when dissolved in water, if they release H plus ion, they are referred to as the Arrhenius acid, and compounds that dissolve in water to evolve OH minus, they are referred to as the Arrhenius base. So therefore phenol is a Arrhenius acid. Now we are going to see why phenols are acidic in nature. Okay, so for this I am going to rub this portion also. Why phenols are acidic in nature? First of all, I am going to draw this reaction. You can see this is phenol. So when it being acidic means H plus goes from the structure of phenol. It is acidic in nature. So now we are going to see why phenols are acidic in nature. For this, I divide the board into two sections. Okay, into two sections I will divide the board. There we go. And now I am drawing the phenol ion. This is the phenol ion. I am going to draw the double bonds. Here is the OH. Here are the two lone pair of OH. So actually OH is a ortho para director and it is a ring activator. So that we will see in a separate section. However, what we have to see here is that OH is having two lone pair of electron. So it can donate a lone pair of electron here, right? Why not? But when it donates this lone pair of electron here, the carbon here becomes unstable. See, the valency of carbon is 4. When this electron pair jumps here, it would become 5, like 2 from here, 2 from here, and 1 from here. So that will be 5. So that would be very unstable. So this pair, this double bond, it would come here. It would jump here as a negative sign. So what we would get is a structure like this. This comes here, and here it is, and here it's a double bond, and OH, oxygen still has one of its lone pair, and because oxygen has lost one electron to carbon, so this would become positive in size charge. One electron is here and one electron here, it's lost to carbon. So that's how it makes a bond, and that's how it gets a positive charge. Now this negative sign outside the ring is also very unstable, because any electrophile can come and attack this negative sign. So that's an unstable situation. So this would come here and become a part of a ring. But when it comes here, this carbon becomes 5, that is unstable situation. So this would jump here. So we get this structure, right? Fine. This still has a lone pair and a positive sign, right? Now this negative charge outside the ring is also unstable. Any electrophile can come and attack, so it gets inside the ring, and when it gets inside the ring, this carbon becomes 5. That's not possible, so this has to come here. So we get another structure that would be like this. So this electron is coming, here is the double bond. Oxygen still has one lone pair and it's positive here. Now this is also outside the ring, it's an unstable situation, it would come inside, but when it comes inside, this carbon becomes here 5, so this would jump back, and now what we get is like this. Fine, that would be a single bond OH. Oxygen has got its lone pair of electron back, so here it is, right? So now I designate them, give them Roman numerals 1, 2, 3, 4, 5. Fine. Note that number 1 and number 5, they are Kekulé structures of benzene, nothing else. Okay. The phenol structures are 2, 3 and 4. Fine. Now we are going to draw the phenoxide ion. So I have already drawn the reaction earlier. We know the phenoxide ion looks like this, right? So this is O minus. Oxygen has its lone pair of electron here also, but now it gives its, because H has left its electron here, so that's why oxygen is negative in sign. So this can be donated here, and when it donates here, the carbon here becomes unstable, so this pair will go here. So I'm going to draw the structure like this. It would come. So that would be O with its lone pair, and here is the double bonds. This is unstable outside the ring. Any electrophile can come and attack it, so it gets inside. When it gets inside, the carbon here becomes unstable. This gets outright. Fine. So now we get something like this. Now this would come here and this pair would come here, so we get something like this. Now this is also not stable, it would come here, and this carbon becomes unstable when it comes here, so this pair should go here, and we get that structure where oxygen again gets the negative sign. I'm going to designate it Roman numerals similar to this: 1, 2, 3, 4 and 5. 1 and 5 are Kekulé forms, right? They are resonating forms, of course. Okay, I mean this whole thing, it can be represented by one single structure, that resonance hybrid structure of phenol ion. So it would look something like this, and here also it would look something like this. Yes, this, and here it will be a positive sign, and here H. Fine. So that is resonance hybrid structure of the phenol ion, and this whole thing can be represented by a single structure, which would be like this. Here also negative sign, and here also you can say that this is the situation. Fine. So this can be represented like this, and this phenol can be represented like this. Okay. Now that is not the main thing. Okay, I'm going to rub this. Just keep these structures on your mind. Okay, because of the lack of space, I intend to rub it. That would be much better, I suppose. Yeah, keep those structures in mind. Okay. Now 1 and 5 are Kekulé structures. Okay, there is resonating structure owing to structure of benzene, nothing else. It not related to so much related to phenol, right? It makes a complete full round here. See the bond here and the bond here, the bond here, bond here, bond here, bond here. So a complete full round has come owing to the structure of benzene. These are cacule forms. Here also there is a one complete round in phenoxide ion. These are also cacule structures. The real structures of phenol ion, the resonating structures of phenol ion is 2, 3 and 4. And the resonating structures of the phenoxide ion are 2, 3 and 4. Fine. Now what is the difference between 2, 3 and 4 of the phenol ion and 2, 3, 4 of the phenoxide ion? What difference do you see? Any guesses? Yes. The 2, 3, 4 structure of the phenol ion, you can see two separate charges, positive and negative. So energy has to, special energy, more energy has to be spent in order to separate the two charges, opposite charges. More energy has to be spent by the molecule to separate opposite charges in the same molecule. Fine. These are high energy structures. Imagine a situation when a positive side of the magnet is kept along a negative side of the magnet. So if they both have a natural tendency to stick to each other, but a special energy is required in order to pull them back, right? If you are holding it, you also need a special kind of energy to pull them back so that they do not stick to each other. Similar is the case with this molecule. It needs a special energy, more energy to not to stick them but to pull them away from each other, right? So the contribution of 2, 3 and 4 to the total overall resonance hybrid structure of the phenol ion is less. What did I say? The contribution of 2, 3 and 4 to the resonance hybrid structure of the phenol ion. We have written a resonance hybrid structure here, remember? That structure, the contribution of 2, 3 and 4 to that structure is very less. Fine. So today I was telling one of my students, so that suppose you are having 5 structures. One is your sleeping structure, the another one is sitting structure, the other one a standing structure, other one is walking structure, and the other one a running structure. And if you are more stable in a sleeping structure, okay, so what structure would you prefer? If you had been given the chance by God, then what structure would you prefer to be most of the time? So his answer was very simple. Sir, I would be in a sleeping structure because I am more stable and comfortable in that structure. So similarly with this molecule, it always wants to be in a stable state. Okay, stable state. These are very unstable states and very high energetic forms. So the molecule spends very less time on these things. Okay, it immediately goes for that. So to the resonance hybrid is more of structure 1 and 5 than structure 2, 3 and 4. Fine. So because these 2, 3 and 4 are very high energetic forms, so it would not be a very energetic form of, it would not take a shape or it would not take a form that would be very highly energetic. Fine. Now for the phenoxide ion, let us look. Structure 1 and 5, it is cacule structure, they are cacule forms. Here structure 2, 3 and 4. Do you see any positive sign here? Any positive sign? No. Only negative sign is there. So, and what do you observe in negative sign? Are they static? No. They are in dynamic motion. So they are actually in resonance. So 2, 3, 4 are resonating forms. Suppose an electrophile is here, it wants to attack. Will it get this negative charge? Never, because once it reaches here, this negative charge would have come here. And once it attacks and comes here, the negative charge would come here. So these are actually stabilizing the overall resonance hybrid structure of the phenoxide ion. Right? It would stabilize the structure of an overall resonance hybrid structure of phenoxide ion. So you can consider resonance to a football match where a very good team is playing. Okay, 5-6 members are playing, they're a good team, and you are a kid before them, you are not so mature player, and you go in between them and you try to take the ball. Is it possible that you will get the ball? Never. In the same case, the electrophile is like that new boy who comes to the football team and he never gets the ball, and because he never gets the ball, the team is stable. So you can say structures 2, 3 and 4 are stable due to resonance or delocalization of electron, and therefore their contribution towards the resonance hybrid structure of the phenoxide ion would be more, because the molecule would intend to be in these forms most of the time. Fine. So in the upper portion of the board, you can see that 2, 3 and 4, they contribute to high energy forms. They make the molecule, the overall molecule, unstable. The lower portion, you can see that structure 2, 3 and 4, they make the lower portion of the board or the phenoxide ion more stable. So what can you conclude from this, that phenol is unstable because of these structures, unstable structures, unstable intermediates, while the phenoxide ion is much stable because the structures, the resonating structures that are involved have resonance in them, and that bring great stabilization to the phenoxide ion. So therefore always the unstable molecule will try to become the stable entity, right? It is the law of nature. Why does water flow from up above the hill to down? Because its potential energy would become less. So this is the law of nature. Every molecule wants to become stable. So now you can draw that reaction. Just observe the arrow when I draw the reaction. What would be the reaction? You draw the phenol like this, and you can draw the lone pair also, and you make a big arrow like this and a small arrow like this. Okay, and more of phenol will become phenoxide ion. More of phenol will become phenoxide ion because the phenoxide ion is more stable. Therefore the reaction will be always shifted towards the front side, right? Towards the right side, the reaction will be favored because this is more stable than this. So this is why phenol is acidic. Now we will see, we will compare it with the acidity of alcohol. Okay, phenol is weakly acidic. Okay, so this has to be kept in mind. Its Ka is 1.3 into 10 raised to the power minus 10. So it's actually weakly acidic, not a strong acid. But alcohol is very weak acid. Alcohol can be said as almost neutral. You know, the Ka of water is 10 raised to the power minus 14, and the Ka of alcohol is 10 raised to the power minus 18. So that is the Ka of alcohol. So it's just like, it's like neutral. It's very weak acid. What would happen in case of alcohol? Let us see. If H plus is going, then RO minus would be formed. Alkoxide ion, this is the alkoxide ion, it's very unstable. See why? Because the electron here is localized. Any electrophile can come and attack. There is no issue to find the electron is exposed. So this kind of alkoxide ion is actually very unstable because there is no delocalization. The electrons are localized at one place, so therefore it's very unstable, and such a molecule is unlikely to come. Okay, and therefore it won't release H plus so easily. So therefore your alcohol is a very, very weak acid. It's almost, you know, equivalent to neutral. So that is the thing. Now we will draw the energy curve. So here we go. This is the energy curve. You draw like that. Okay, and now you draw the potential energy here. I am writing it as PE. Okay. Now you can draw your ROH here. So the ROH becomes RO minus and H plus. It has to go from this energy level to this energy level. So you require at least this energy to reach here. Similarly, you draw the phenol. little below ROH. So this is the phenol, fine, and it's this, the energy level is this, suppose, okay, this is the energy level, and you draw the phenoxide ion here, fine, H plus, and its energy level is like this much, suppose, fine. So to come from here to here you require this much energy, delta E2, this much energy you require. Draw a line like this. The phenol should have been here actually, but it's lower in energy. Okay, the bar is lower. This is because of resonance stabilization in phenol. Resonance stabilization in phenol, right? So it has stabilized the phenol here, okay, and you can draw a line from here to here, fine. So the phenoxide ion should have been actually here, right, in the same place, but it is not here. It is lower in energy, its bar is lower, and this lower is because there is resonance stabilization in phenoxide ion, right? Fine. I hope you enjoyed the class. Please subscribe the channel. Thank you very much.